So to answer this question, I thought I'd make a video to talk through my reasoning behind how I figure out which compounds are soluble and insoluble, and then for the later part, for the redox rules and how to handle those. So first and foremost, these questions involve you have an understanding of a few things: polyatomic ions, solubility rules, and redox rules. You need to know those three things to answer these questions. The polyatomic ions you can see over here on the right on the screen right now. I think it's not off the screen. It's all off the screen for me because my computer's old. You should have these memorized. You should be able to see sodium sulfate. You should see sulfate and automatically know what that is. I'm going to kind of assume you do, but I'm going to leave the polyatomic ions on the right for you. That's something you should memorize. Another thing you need to know is the solubility rules. So I have those up here, and this is the basis for these first two questions. To understand if something is soluble, you need to have memorized, especially depending on what chemistry level you're in. Sometimes they ask you to memorize it. Sometimes they'll give you a list. You'll need to know how to use the list. You need to know which compounds are soluble or not. So let me run through these really quick. These guys are always soluble. Anything made of an ion of lithium, sodium, potassium, or ammonium will always be soluble. Sometimes people say group 1 on the periodic table because lithium, sodium, potassium are all in group 1 on the periodic table. And that's a pretty good rule, although the bigger ones on the bottom can get a little iffy. But generally speaking, group 1 metals are soluble, as well as ammonia. Additionally, for negative ions, nitrates are always soluble. And I'm not so sure about acetate. I think that's actually not correct. I just pulled this off the internet, this picture. So nitrates are definitely always soluble. Acetates are mostly soluble. There are some that aren't, though. So I'm going to go ahead and cross that off. Moving on, we have some group 7 ions here. These are your halides. Halogens turn ions into halides. So we've got chloride, bromide, and iodide. Generally speaking, these are soluble with almost everything. So if you see something with chloride, it's probably soluble, like aluminum chloride, AlCl3. The exceptions to that are listed in this table: silver, lead, and mercury. So this would be soluble, but like silver chloride, AgCl, that would not. Okay, I'm going to have to scroll because I can't see anymore. Scroll. There we go. Sulfate, generally soluble as well. It's soluble with almost all ions. There's some exceptions to sulfate, just like for the halides, and they're listed here. Notice calcium sulfate, that's going to come up in a second. And then finally, you've got some other ions down here near the bottom. Carbonates, phosphates, hydroxides, and sulfides are generally insoluble. So don't let this kind of confusing nomenclature here confuse you. These guys pretty much don't dissolve. The exceptions are the things we've already talked about. Here's our group 1 metals, so they'll be soluble with those. All that means is these rules up here at the top trump the rules down at the bottom. So it's important to know these rules. Just memorize them. That's kind of all you have to do. There's some tricks and like some charts that help. So let's talk about first the solubility here. I've gone ahead and written the reactions. If you can't write these reactions, well, that's kind of what I'm going to talk about here. So the species present in the net ionic equation for the reaction of sodium sulfate and calcium chloride. So first of all, sodium sulfate is written like this because sodium has a +1 charge and sulfate has a 2- charge. That means I'm going to need 2 sodiums and 1 sulfate. Calcium chloride is written like this because calcium has a 2+ charge and chloride has a 1- charge. These charges, by the way, for sodium, calcium, and chloride, I got those from the periodic table. Sodium's in group 1, calcium's in group 2, chlorine is in group 7. So that's how I know these charges. Hopefully you've kind of know that already. So now that I know that this is going to be a precipitation reaction because we're talking about net ionic equations here. So the sodium and the chloride are going to pair up to make sodium chloride. That's a 1-to-1 ratio because sodium is +1, chloride is -1. And calcium sulfate will pair up in a 1-to-1 ratio as well. 1 calcium and 1 sulfate because calcium is +2 and sulfate is -2. To balance this equation, I would need 2 sodium chloride. But we're asking about the net ionic equation. What that means is we need to recognize a precipitate. So let's look at our solubility rules. Sodium chloride, well, this is rule number 1. Anything with sodium in it is going to be soluble. You can see that here in the first rule. There's sodium. So that means he is aqueous. Now, calcium sulfate, if we look back at our sulfate rules, if I could scroll, here we go. Calcium sulfate is actually insoluble. Sulfates generally are soluble, but except with these guys, and calcium is one of them. So that means calcium sulfate will be insoluble, which means it's going to get a solid. And that means to write the net ionic equation, all we need is the precipitate and the ions we use to make it. So that means for question 1, the ions present, or the species present, will be calcium, sulfate, and calcium sulfate. Sodium sulfate is aqueous, so it'll be ionic, aqueous in solution. And sodium chloride is aqueous, and calcium chloride is aqueous, which means the sodium ions cancel and the chloride ions cancel, which means this whole term cancels basically. Okay, so that was the first one. And that's the general idea for writing the equations, is you make sure your charges cancel and you go from there. So I'm going to go through that a little bit quicker in number 2. In this case, we've got 3 equations. That's why I've got to go through it a little quicker. So we've got the first one, and the way this was written is kind of hard to interpret. That's the first one stops there, the second one stops there, and the third one's there. So first we have ammonium hydroxide, which looks like that. That's a +1 and -1 ion. Those are in my polyatomic ions over here on the right. And then copper 2 nitrate. Now copper 2 has a 2+ charge. Nitrate has a -1 charge, which is why I need 2 polyatomic nitrate ions to cancel that 2+ charge. Now the double replacement will go the same way. The negative and the positives will flip. So now I'll have copper 2 hydroxide and ammonium nitrate. Now this guy, ammonium nitrate, he follows both of my first 2 rules. Maybe I can clean this up a little real quick. Yeah. So I've got ammonium and nitrate both here. These guys are both always soluble. So that means this is going to be aqueous. Copper hydroxide, however, that looks like a hydroxide, and that, can I scroll please? Thank you. There he is. Hydroxides are always insoluble with any ion that isn't one of these. Copper's not in here. Therefore, copper hydroxide is a precipitate. So, boom, he's one of our precipitates. Okay, I'm going to kind of skip through the making the ionic compounds now because I don't want this video to be too long. So now we've got potassium carbonate and magnesium bromide. When they react, we'll make potassium bromide and magnesium carbonate. Potassium is a group 1 metal, and potassium is one of the ones that's always soluble from our rules. Bromide also is one that's always soluble. So then we've got magnesium carbonate. We better check on carbonate. Looks like carbonate is insoluble with almost any other ion. These were the exceptions. Notice that we had, what did we have? Potassium carbonate to start. And this was aqueous because potassium is always soluble. So that's why the carbonate was okay here, but paired with anything else, he's going to be solid. So solid magnesium carbonate, and we had the solid copper hydroxide up here. So that's why magnesium carbonate is my precipitate here. And then finally, we've got sodium oxide, soluble because of sodium, and aluminum sulfate. Most sulfates are soluble, actually. And when that reacts, the ratios here are a little bit weird, but we've got sodium sulfate and then aluminum oxide. Now again, sodium is soluble because all sodium is soluble. So he's aqueous. But then the aluminum oxide, there's not even a rule for aluminum oxide. So the general rule is if there's an ionic compound you don't have a rule for, it is going to be a solid, not aqueous. So this is my solid precipitate, and we can see he's right there. So those are my 3 precipitates from this equation. Finally, we have the redox stuff here. I'm going to scroll down a lot here. I shamelessly stole this from Tyler DeWitt. I want to make sure I don't, I will not acknowledge that I took this from his video. He has great videos that go over redox, so I'm not going to do that here. Look up Tyler DeWitt redox if you want a little more info on that. What I do want to focus on are these rules right here. And then right here. So these are the rules for identifying oxidation states. These are things you should memorize. For example, oxygen is usually -2. You should always know that. Fluorine is always -1. Monatomic ions have an oxidation state equal to their ionic charge. So those are rules you should have memorized, just like the solubility rules. So in this reaction, we want to figure out what is reduced, what is oxidized, what's the oxidizing agent, what's the reducing agent. First, we need to assign oxidation states. The first thing we can do is notice oxygen, and oxygen is always -2. So the oxidation state of oxygen is -2 in both of those compounds. Next thing I noticed is bromine or bromide. And then we can see here that halogens usually have a -1 charge. The exception is that it's positive with oxygen, but bromine isn't with oxygen in either of these compounds. So bromine is going to have a -1 oxidation state. Okay, so that means we're not concerned about oxygen or bromine. Their oxidation states didn't change. So what did change? Well, iron 3 oxide over here is going to be the iron with a +3 charge. And since that is an ionic compound, a monatomic ion, the oxidation state is equal to its charge. So iron in this compound has a +3 oxidation state. Well, what about over here? Well, here it's with 2 bromines. That means it has a +2 charge. And we know this, by the way, because over here, the 3 oxygens give overall -6 charge. To cancel that, I'm going to need +6 bonded to it. +6 divided by the 2 iron ions gives me a +3 charge. The same is true over here. 2 bromides with a -1 charge each. That means I'm going to need 2 positive charges to cancel them out. That means this 1 iron ion must have a +2 charge, and therefore a +2 oxidation state. So by that reasoning, we can do the exact same thing with 10(2) bromide. That has to be +2 as well. And then over here, this 10 has to be +4 to cancel out the 2 -2 charges from the oxide. That's -4 overall, so this is +4 overall. And that's, by the way, following this rule, the sum of oxidation numbers for a neutral compound has to equal 0. Since these are all neutral ionic compounds, they all have to add up to 0. Okay, so now that we know the oxidation numbers and we don't care about oxygen or bromine, we can erase those to make this a little neater. And we can see what's really going on here. The iron went from a +3 to a +2 oxidation state. That means the oxidation number was reduced. Well, that means it was that means iron was reduced. That's going from a +3 to a +2 oxidation state. If your number gets smaller, it's a reduction. If your number gets bigger, it's oxidation. You can also think about it as iron accepted electrons there. So that means it was reduced. 10 bromide, well, the 10 started at +2, and then it went up to +4. That is an increase in the oxidation number, which means we lost electrons. So that means 10 was oxidized. Now, when we're talking about the species being reduced and oxidized, you usually want to say the entire molecule. So I think it's different depending on your teacher. But if I was saying which species was reduced, honestly, I would say, well, honestly, I would probably just say the iron ions. But I think what they're looking for here is Fe2O3 was reduced. And then it says what species was oxidized. It's the other one. It's 10(2) bromide. Okay. Now, the reducing and oxidizing agents are the things doing the oxidation. They are not the things being oxidized. It's really backwards. But think about it as an oxidizing agent causes oxidation by accepting electrons that the thing getting oxidized gives away. Likewise, the reducing agent gives away electrons in order to reduce something else. So you can think about it in terms of the electrons, or you can just look at the opposite thing. So, and in this case, we really want to focus in on the ions that gave away electrons or received them. So let's hone in on that. Let's see. So iron oxide was reduced. That means the iron ions received electrons. This means this was the cause of something being oxidized. The tin gave away its electrons to iron. If iron wasn't there, oxidation of tin couldn't happen. That's why we consider iron to be the oxidizing agent. And notice that it is flipped. Specifically, it's iron 3 because it's in the reactants right now, iron 3. And then is iron 3 an option? Yeah, there it is, number H. Okay. And then likewise, the reducing agent is going to be the tin ion because it gave away electrons to reduce the iron. So 10(2) was the reducing agent. Sorry this video was so long, but I really wanted to focus in on all of the rules you needed to know and how to visualize what's going on there.